Okay, welcome everyone to Talks at Google. We are very privileged today to have with us Sabine Hossenfelder. Sabine is a theoretical physicist who studies quantum gravity, but she is much more than that. She's also a prolific blogger. Her blog BackReaction, which she started in 2006, has had over 7 million views. She is also a contrarian author, where in her book Lost in Math, she pushes back against the physics community, claiming that they have been too focused on beauty and that they might be working on the wrong problems. And she is also a YouTube star, where she is the content creator behind her channel Science Without the Gobbledygook, where she has a variety of videos on various topics in science, many times with her own unique soundtrack. So let's welcome Sabine. Sabine, great to have you here. You're such a unique person. Why don't you tell us more about yourself and how you came to be who you are?
Yeah, well, you gave a pretty good short summary. So maybe I should start with explaining where I currently am. So I'm in Germany now, back in Germany after a long time of traveling around the world. And I'm a research fellow at the Frankfurt Institute for Advanced Studies. And I'm also originally from Frankfurt, so I've been traveling around in a big circle. And pretty much all that you just said, like the book, the blog, the YouTube channel, and so on, came out of my PhD thesis in a not very straightforward way. So I wrote my PhD thesis on particle physics, phenomenology beyond the standard model, the production of tiny black holes at the Large Hadron Collider in particular. And that was like in the years 2000 to 2003, when it was a really popular topic, you know, this idea that the Large Hadron Collider would be able to create these tiny black holes. It attracted a lot of attention. Maybe some of you will remember that there was a story, someone tried to sue CERN over trying to destroy the world. It made big headlines a few times. And yeah, so that was the stuff that I was working on. And now the story with the black holes was that if gravity works the way that Einstein taught us, so we have 3 dimensions of space and 1 dimension of time, and they're curved and so on and so forth, then you can't create black holes at the Large Hadron Collider. It's just that the energy you can reach in these collisions isn't remotely high enough. But if the universe has additional dimensions of space, and these are fairly large, then you can do it. And the reason is that the gravitational interaction gets much stronger on short distances, so it becomes easier to create these black holes. But as I said, you need these large extra dimensions. And that was popular at the time because, well, for one, no one really knows why the world has only 3 dimensions of space. Could be anything for all we know. So it's a reasonable question to ask, just generally what would happen if the world had additional dimensions, but also because string theory predicts that there have to be additional dimensions, 6 additional dimensions of space. And now the thing is that to be able to see these tiny black holes or other signatures of these 6 dimensions at the Large Hadron Collider, they have to be at exactly the right size. So if they are too large, we would already have seen them. And so that's just ruled out. We would have seen them at particle colliders with lower energies. And if they are too small, then they are beyond the reach of the Large Hadron Collider. And that's actually what was assumed for a long time, which is why no one ever thought about this before the year 2000 or something like that. So that brings up the question, like, why are they exactly in that range where you could see them at the Large Hadron Collider, but they would not be out of reach and we would have to build a bigger collider? And I remember giving a talk about my PhD, like it was the first talk that I was giving at an international conference. And someone asked me this question, like, how is it that they are just exactly at this energy range where we can see them at the Large Hadron Collider, but not above that? And the answer I gave was the same answer that everyone gave in their papers and in their seminars, which is that if the energy required would be much higher. They would be beyond the mass where you would discover the Higgs boson, and that would no longer be natural. So they were introduced to solve this naturalness problem in the standard model. And I suppose I'll have to give you a little bit background what this naturalness problem is all about. So the physicists call a theory natural, roughly speaking, if it doesn't have numbers that are either very large or very small. Or if they are very large or very small, they need to have an explanation. An explanation can, for example, be a symmetry. Supersymmetry, for example, can explain why a number is very small, that kind of thing. And the standard model is not natural in that sense. There are two numbers in the standard model that are not natural. One is the mass of the Higgs boson, and the other one is called the theta parameter, which is a different story altogether. So when it comes to the Higgs mass, the story is that it should actually be much larger than what we observe, and it requires an explanation why it's small, that the standard model does not deliver. And in order to fix that problem, which looms large in the minds of particle physicists, you introduce new physics. And that new physics can be supersymmetry, or it can be other additional particles, or it could be extra dimensions, doesn't really matter. But the point is, it has to become relevant at the same energy that you discover the Higgs, because otherwise the naturalness problem comes back. And that was the entire argument why particle physicists thought that some new physics besides the Higgs boson has to appear at the Large Hadron Collider. And that's why you read all these headlines about supersymmetric particles and dark matter, extra dimensions, parallel universes, gravitons, tiny black holes, all that kind of stuff goes back to this naturalness argument. And technically, if you look at the mathematics, it's not a difficult argument. So that was not my problem with it. My problem was that I didn't really understand why you would believe the assumptions that lead to this mathematical conclusion. And so after I gave my talk about the black holes and I answered this question, the person who asked the question was like, like this explains everything. And, that it was fine for what the talk was concerned. But I went away feeling like really, really stupid for giving this answer when I didn't really understand what the rationale was for this naturalness argument. And so I started looking into it. And I looked at the literature. And it turns out that if you look at the literature, like where this argument actually came from, people were really careful pointing out that it's really ambiguous. It's arbitrary. It relies on arbitrary assumptions, which was exactly the problem that I had. So it's not a good scientific criterion. It's actually a metaphysical criterion. And so for me, this caused like a big problem because I had written my thesis on this, but now I actually didn't believe anymore that this was like a sound scientific argument. And I began asking people about it. Like when I was at a conference or something, I would ask them about this, how do you make sense of this? And, they would try to explain it to me. But at some point, they kind of realized that they couldn't really answer my question. And some walked away and others became a little unfriendly. But I never really got an answer. And now you have to understand that at this time I was a young postdoc, so my self-confidence wasn't exactly the best. So I was under this impression like I'm just stupid, like, all these 10,000 people have understood it, but I can't understand it. What do I do now? And well, my personal conclusion was that I would stop working on it because even though I didn't have the best self-confidence, I couldn't see anything that was wrong with my argument, and no one could tell me anything that was wrong with it. And so I got a very prestigious fellowship, a scholarship from the German Research Foundation, which I think is probably still the most prestigious one that the Germans have. It's called the Scimeter Fellowship. And it's a 5-year thing, gives you funding for a whole group. So it's kind of, the Germans don't really have tenure track, but that's kind of as close as you can get to tenure track, is getting this fellowship. But it would have required me to continue working on this for 5 more years. And I just didn't want to spend 5 years of my life working on something that I didn't really believe anymore made scientific sense. And so I declined it. And then I started working on something different. And then I started blogging. Right? So I started writing about it carefully, because I was still thinking that I'm dumb, I don't understand it. And that was long before the LHC turned on, by the way, like years before that. It was 2005, and the LHC wouldn't turn on until 2009. And but as you all know, what happened was the LHC turned on, and they indeed didn't see any of these things that I'd been hoping for. They saw the Higgs as anticipated, and that's a huge celebration, a breakthrough discovery. There's no doubt about it. But they didn't see any supersymmetric particles. They didn't see dark matter. They didn't see gravitons. They didn't see black holes. And I was thinking, and now I feel terribly naive for this, I was thinking they would realize that this argument was just rubbish. They would wake up and say, oh, all right, it was really not a scientific argument. We have to stop using it. But that never happened. Instead, what happened was that, at first there was a certain denial, I would say. It was like, okay, we haven't seen it so far. Certainly it will show up in the next run, with the next data analysis, whatever. And that continued to not happen. They didn't see supersymmetry. And then at some point, the argument became, maybe it needs a little higher energy. And maybe this naturalness argument works a little bit different. It's a little bit more complicated. And at some point it was just completely foreseeable that the way the argument would go at some point is we need a bigger collider. And it was like 2 years or something after they discovered the Higgs, so it would have been 2014 or something. And I thought, I have to write a book about it. Like, the public needs to know that these arguments they're not sound science. These are arguments from beauty. It's wishful thinking that they might be seeing these particles. And so that's when I wrote the book. And then, of course, what happened was, as I said, it was pretty foreseeable they would start arguing we need a bigger collider. And so I became the person to speak out against this bigger collider, and it certainly hasn't made me many friends among particle physicists.
I see. And then, so I see. So how does your, I guess, pushback against the scientific community, how did that lead you into, scientific metrics, citation metrics, things like that?
Well, this is something that I've, independently of that, been interested in for a long time, because I've always felt that scientists generally, not just particle physicists, don't take into account sufficiently that they're part of a big group of people, and the interaction with other people, like all this information exchange, which has now been accelerated with the internet and so on, it influences how they think of themselves, what they're interested in, and so on. And in the end, how you deal with that is, in my mind, it's a technological problem. Exactly how do you know what you're influenced by? How do you make sense of this? How do you filter your information? That whole story, which was to me always something that you can address, to some extent, algorithmically. And so I'd always been interested in the question, like, how do you measure scientific success? And how do you filter this information, and so on and so forth. And this is something that I've been looking into for quite some time. One thing that I've been talking about, for example, I remember when I was at Frankfurt Institute already, so that would have been 2007 or something, was that it's always struck me as a really bad idea to assign people to specific groups. Like, if you join a department or an institute, they'll put you in a group on cosmology, say, or particle physics, or quantum foundations, or whatever and now you have this label on your forehead that says you're a string theorist, or you're a condensed matter physicist or something. And there's a lot of research on the group psychology that tells you that the moment you assign people to a group, they'll start identifying with that group, and they'll defend, the identity of the group, basically. And I think that a lot of the hostility which we saw, like after Lee Small and Peter Voigt published their books that were rather critical of string theory, is tied to this very strong group identity that seems to be particularly pronounced among string theorists. And so one of the things that I proposed that would be working against this is just to not cluster people in groups. Like if you look at the website, you get a list that says, oh, these people are in the string theory group and these are the particle physicists and so on. But instead, use tag clouds, as you see, as people sometimes use summaries of stories or on their website or something like that, that would just show you the whole variety of things that people are interested in, which most of the time is not really very narrowly on one thing. Like I wasn't just purely a particle physicist, I also did something on general relativity, modifications of general relativity, quantum gravity is what I did later, quantum foundations, all that kind of stuff. So you want to have a visual representation of the whole breadth of someone's research. That's what I thought these tag clouds can do for you. And I put this forward to the IT people at Perimeter who quite liked the idea, but then the administration wouldn't go with it. And I tried this again at the next institute where I was in Stockholm. And again, the IT people thought it was nice, because I suppose they just like to play around with things. But in the end, it didn't come to being. And so this was also one of the first things that we did on the Scimeter side, to create these keyword clouds, which I thought, that they make a practical difference for how people represent their research. They no longer have to assign themselves to a particular group. And so this is one of the things that I've been interested in, but also it's kind of obvious, if you think about how I came to write my book, that I was really worried about how something like this could possibly happen. Like, how can you have a community of thousands of people who will all repeat the same argument, even though it's like obviously wrong? Like, this is what I would say. It's like obviously nonsense. And, I would bet there are particle physicists listening right now who still don't even understand what I'm talking about, because they would never read my book. And they still totally don't understand how could possibly something be wrong with the naturalness argument. But yeah, that's how it goes. And I think what's going wrong there is that people, they have this really close community. They don't listen to people from outside. Like, this is something, for example, that philosophers could have, corrected if philosophers would have looked at it, and if particle physicists would listen to philosophers. So but it didn't happen because this community is just too closed. And the other thing which also plays into this is if you ask, like, why were there so many people writing all these papers about predictions that we now know are wrong? Like, there are literally 10,000s of these papers, to which I have also contributed, right, with my PhD, and these are still my best cited papers. Like, that's the tragedy of it. All this stuff of black holes at the NHC is still my best cited work. I still sometimes get invitations to talk about this. I mean, it's like really bizarre. And so, if I had actually taken this scholarship and had worked on it, I'm pretty sure it would be tenured by now. But I'm not, because I didn't want to work on what was politically probably the smart thing to do. And why does this happen? It's because people have to pay a lot of attention to what they can get published and how well it will be cited. And that's a big problem. And so that's the other thing that I wanted to address with this Scimeter website.
I see. Great. Makes a lot of sense. Why don't we actually take a look at Scimeter? Maybe you can give us a demo of what it looks like, how you use it, and how others can use it.
Yeah, right. So hang on, I have to find the... Okay, can you see my mouse cursor now?
Yep.
Okay, wonderful, great. So yeah, so this the website is so maybe I should start with saying this. I've been told it's not a website, it's a web interface. Okay, it gives you access to a database on which you can do your own analysis. So that's the idea. It's called Scimeter.org. You can basically right now look this up. And try it out for yourself. But we've been working on an update, and what you see here, you see this staging in the back. So this is the updated website, which I will show you now, parts of which are not yet live, but I hope we'll get this online, maybe in the next month or something like this. So I want to start with explaining you what you would now see on the website that you can access yourself, which is only the analysis we have done with the archive data. So you see here we have this, it says archive here, and there's this little archive logo. So with the update, we'll allow people to switch to a different database, which I will tell you a little bit more about later. But one thing you can do with the archive data is what I just told you about briefly, are these keyword clouds. And this, it really uses only the papers that are on the archive. So, and that's of course some kind of a limitation, but I guess that most people who are listening have papers on the archive. And so this will create a visual representation of all the topics that you have worked on that you have on the archive. And so let's try one example. Brian Green.
Famous string theorist, by the way.
Yes, which you will see. Oh, so you get this pop-up. Sometimes there's more than one author because some people have middle names. They're not consistent about how they use them. You can join them together. And okay, so there's Brian Green, and you can see immediately just by looking at it, right? It's the string theorist,
right?
So and you get a pretty good idea what he's working on, and there's also the color code, which the color code is added in the bottom left corner. Tells you how recently they've been working on this. So the more reddish stuff is more recent work. And the cooler stuff, the bluer stuff is the older stuff. And there, you can customize this a little, change the size if you want, and download this in various formats. Play around with this a little. You can kick out somewhat if you don't like them, and then you can put it on your website or on your CV or something like this. And there's some other things that right now you can only do with the archive data. One is, for example, you can find similar authors. Like if you're, you want to know what other people are working in my research area who have similar interests, like working on similar stuff, you can just enter your name or somebody else's name, and we go through the database and look for that. So let's see. Let's use Faye. Yes, the same thing. Yeah, so here we have the list of the similar authors. It's kind of funny, I know all these people. So this gives you an idea, like, for example, if you want to organize a conference or something, and you're looking for people with whom you might submit a proposal or something, who just share your research agenda, then that's something that is like really, really practically helpful, I think. And another one that we have here that I want to show you are topic matches. You can just look for people who have worked on a particular topic. Again, that's something that you might want to do if you're organizing a conference maybe, or if you're say you're a science journalist and you're writing about a particular topic, you're looking for someone to interview, that might be helpful. Like suppose, I don't know, you want to organize a conference on dark matter and what they do to galaxies, something like that. Galaxy. And then it will spit out the best hits to that combination of keywords. And you can also adjust the weights if you want. You can play around with this. If you have a third topic of your conference or something that's not all that important, you can give it a lower weight. These are all applications that right now only work for the archive data. And then we have the metrics, the do-it-yourself metrics, which work for the archive and for the new database. And I will show you those with the new database. So it says here MAG, that's the Microsoft Academic Graph. That's a larger database. So the archive database has obvious limitations. One is that it only covers certain areas of science, but also it only has papers that are past 1994 or something. So if you have authors who have a lot of their important work before the time that the archive came online, or they work in fields where a lot of the papers are not on the archive, then the archive data will give you really not very representative results. It's just not particularly useful. And the data from the academic graph, it covers all fields of science. So that's the benefit of this. Maybe I should briefly give you the overall motivation for the do-it-yourself metrics. So what I've seen a lot of times sitting in committees where you had to hire someone or stuff like this, is that people fall back on the simplest measure for academic productivity that you could possibly think of, which is the number of papers. It's the number of papers in journals with a high impact factor, and it's the number of citations, and then there's the H index, which is derived from this. And I think the major reason people always fall back on these measures is that they're readily and easily available. And most of them, at least those that I've been in contact with, know full well that these measures have severe shortcomings and they're actually using them is not beneficial for science overall, because it strongly encourages people to work on really popular topics, which in the long run can just hinder progress. But they keep using them. And why is that? It's because it's the only measures that you can just easily read off from someone's, Google Scholar page, or from Inspire, or just from their CV by counting the papers, or sometimes you actually have to list the number of citations and so on. So the idea with the custom metrics was to enable people to produce their own measures, which would be more realistically realizing their personal idea of what it means to do good science. And it's not only for your personal, but you may have an institution that has a particular goal, that has a particular mission. Some people might be looking for someone who's very specialized in a particular topic because they have a niche to fill. And then others, they may be looking for someone who has very broad interests, who can maybe help to glue together a faculty that's a little bit fractured, stuff like that. So it's not that that there's only one style of doing research, and there are very different ways that you can think of that you might be looking for. And so to show you how this website works, I've used the names that you sent me, and I added them to an author list here. But you can also do this yourself. the idea is that you can create here a list of people. In principle, you can upload a comma-separated file, like if you have a list of applicants for a position. But you can also create it from scratch. You give the list a name, and then you add the authors here. To save us some time, I did this with the names that you gave me.
Yeah. By the way, for people who don't know, these are the Turing Award winners from 2018: Yoshua Bengio, Jeffrey Hinton, Jan LeCun, pioneers of AI, and the most, among the most highly cited of machine learning researchers. So I thought this would be a good chance to see how these distinguished people would stack up with Scimeter. So let's see.
Yeah, so what you see here, this number, that's the H index, which I use as the default metric of this author list. And I cross-check this with a Google Scholar, which gives pretty much the same number. So that's actually pretty good. So quite happy about this. One metric that we did ourselves, which is on the list that you can choose instead, is what we call the normalized H index. We added this because it's one of the things that people have asked us for most frequently. It's that you just normalize the H index to the number of people who work in the field. Is because otherwise you can't really compare it. Like if you have someone who works in a huge field like computer science and you compare that to someone who works on a really niche topic, like, I don't know, superdeterminism, like where there may be 3 people working on it, it's kind of really unfair to compare these numbers. It doesn't really tell you anything. And so you can just click on this and you get the normalized H index. In that case, it doesn't really make a big difference because they all work in the same field. But if you compare people from different fields, then it can really entirely change the game. And I have another example here, which is the number of single-authored papers, which is interesting because you see it flips this order, right? So this Joshua person becomes the second, and Geoffrey moves up because he seems to be working a lot alone. He has a lot of single-authored papers, and for some people that might be very interesting information. If you know how much of the work people do alone or work in teams with each other. And you can also create your own metrics, basically everything you want in principle. Then in practice there's some limits to what you can input here, but that's the idea. You might, for example, let's say you want to do something like the number of citations for a paper per author. So if a paper has more than one author, you want to divide up the citations. And that would be, you just use these indicators here, that would be unset divided by not. And then you take, let's say, the mean value. And yeah, you save that, and then it will appear in your list of metrics.
See, so that's the mean over each paper. So each paper has a citation.
Exactly. Okay. Yes. And that's now your new metric, and all you have to do is click on it, and that will do it for you. In this case, or did it actually change something? It actually did, didn't it?
I think it did. Jeffrey's number is now very high.
Yeah. Again, that's because, as we saw previously, he has a lot of single-authored papers, and so basically, what happens if you divide by the number of authors is that it dilutes the teamwork, kind of basically. So yeah, so I think that will give you an idea for how it works. You can, in principle, if you have created your own metric and you're fairly happy with it, you can submit this for approval, and if we approve it, then it will appear on the list of predefined metrics, so other people can use it. and you can rate it, give it stars. There very few people have actually done it, but in principle, the functionality is there. You can also say you have a long list of people, your candidates, like the 100s of them. You can order them according to different metrics that you have done here, and then you can download and save the newly ordered list and then share them with other people. So yeah, I think I'll stop here. Do you have any questions that I could just that I should be showing you here?
Well, I'm curious. So like, so in terms of the day-to-day life of a researcher, especially say in machine learning, where there's hundreds of papers uploaded to the archive every day and thousands of papers submitted to conferences, is there any kind of quick use case that you can think of that this tool might help with for researchers who are trying to stay afloat with all their research?
Well, so this do-it-yourself metrics thing is really aimed at ranking researchers or institutions at some point, because in principle you could add groups of people, and then this is not presently possible, but in principle you could do something. I think for the day-to-day life, these options with the similar authors and the topic matches are really, really useful. I actually use them myself, if I have to organize a conference or something, or you're wondering like who are the people who have worked on this. The computer science is covered by the archive, so you don't actually need the new database. You can actually do this with the archive database already.
Mm-hmm. Yeah, can you give an example of how you've sort of used it in practice for your own the day-to-day research?
Yeah, I actually do this. Like if I organize a conference and I don't, how do you find out who to invite? The thing that people normally do is they brainstorm. Like, who are the people I've interacted with in the past? Whose papers have I read? And then you ask your friends, right? Who else could we invite, the people you're organizing the conference with? But it's a really biased procedure, because there might be, I don't know, a big research group in China or something who you just never heard of, and you wouldn't invite them because they're not in your network. And I think that this tiny little tool, which I think is so obvious, it blows my mind that you can't do it on the archive itself, will just give you the list of authors who have worked on a particular topic, and it will help you to discover new people to invite to your conference. And I've actually done that in the past. And it's also it will, as I said, you know that I do some science writing, and I sometimes interview people, and it's sometimes I just don't know who are the right people to contact, like who are the experts on that topic, and that tool will help you. And also, if you're like, as I said previously, briefly, if you're looking for collaborators, or you just want to figure out whose papers to read, then you might just want to look for what other people have done very similar work to yours, because those might be people to follow.
I see. Okay, great. This is great. I think this was a really great sell for Scimeter, and I hope people check it out. Let's maybe zoom out a bit, because you started off talking about some of the problems with the ideas that have been circulating in the physics community for a long time, and you've explained how these citation metrics can help to alleviate some of the systemic biases in research. What do you see as sort of maybe the future of scientific research, where it's going, and maybe how it ought to course correct, the way you see it?
Well, that's a pretty big question.
Sure, but maybe some general thoughts.
Well, I wish that scientists generally overall, not just particle physicists, would be more self-aware of being part of a large community, and how this affects their work and their thinking, and how it can also bias what they work on, what they think is interesting. And that's like really, really lacking. I think it's something that people should be taught with the education, and that we have to be much more mindful of when we use these really, really naive measures for scientific impact.
Mm. Okay, well, before we go to the Q&A, I just wanted your opinion. 2019, Google announced that they had a huge quantum computing breakthrough, that they achieved quantum supremacy. That was this result that they had performed a computation that is efficient for a quantum computer, but not for classical computers. Do you have any comments on that? And will you be making a YouTube video on that possibly?
I did do a YouTube video about this, like purely coincidentally, briefly before the actual announcement, where I basically, the video explains what is quantum supremacy and what does it mean and what does it not mean. And I mean, I'll say the obvious, it's a remarkable achievement. I'm a theoretical physicist, everybody who can actually do something in the laboratory, even better quantum things. I'm super impressed. So yeah, I think it's pretty cool. I'm also working on a video where I'll be talking about what has happened in quantum computing since, who's working on what's happening, what's the current standard, what are different companies aiming at. Yeah, I'll be talking a little bit about this probably in the next month or two.
All right, great. Well, I guess hopefully people will find that on your YouTube channel in the near future. Okay, well, let's thank Sabine for explaining her work and giving us such great insights. And I guess we should probably go to the Q&A and see what kinds of questions we might have. Okay, great. We already have a question here by Sujit. What does the Higgs mass parameter in the standard model Lagrangian look like, knowing its pole mass?
What does the Higgs mass parameter look like? Well, the Higgs mass is just a parameter. It's mh, and you measure it. I'm not sure I perfectly understand the question. It's like you can't actually calculate the Higgs mass from any known theory. It's just a free parameter in a standard model, like all the masses of the other particles, and you go and measure it. Okay,
let's see if we have any other questions at this time. Okay, next question by Jose. Could you tell about superfluid dark matter? Do you foresee any experiment which could confirm it, possibly a better investment than bigger colliders?
Yeah, so I have a 1-hour talk on that topic. So I can talk about this endlessly. The brief answer is, it's hard to confirm anything in science, but I think that there may be observations that would pretty clearly speak for superfluid dark matter. And maybe the most obvious one is that if you're looking back in the formation of galaxies, then at some point this phase transition has to happen. And that's very different from normal cold dark matter where you don't have phase transition. And it's also something that you wouldn't expect in modified gravity. But the current data, on galaxy formation isn't good enough for that. But in principle, it's something that you can look for. So this is one of the possible ways that you can test it. And well, as I said, I have a particle physics background, so I'm of course always wondering, like, can you actually detect it in the laboratory? Like, is there an experiment that you can make? And this is something which I'm currently working on with my student, and I hope at some point the answer will be yes, we know how to probe it. But right now, I don't know. It may be that it's just too damn weakly interacting, and so it's unfeasible to detect it. But I hope that I might have something more positive to say in the future.
Okay, another question from Kaushik. Hi, Sabine. Big fan of your work on science communication, asking hard questions to your community. Do you think our current investment in fundamental physics matches expected return for humanity?
Well, that's a hard question. I wouldn't really know how to quantify that. I wouldn't even know how to begin thinking about it. So I think I'm a little less ambitious with the questions that I ask, and so this question seems to me it's very much a question about politics. Like, how much money do you invest into the foundations of physics to begin with, given the expected payoff that you have, like maybe 1,000 or 2,000 years from now. And I'll leave this to an economist to figure out how to quantify that. To me, the question is a simpler one, which is if you give the community who works on the foundations of physics as much money as society is currently willing to put into it, how do you invest it best? And to me, the answer is not building a bigger collider, because that's currently just not a particularly promising way to invest this money. There are just other things that would be a better investment and that are more likely to lead to a payoff.
Okay. Sabine, I have a question, actually. So, you've talked a bit about, physicists getting distracted with things. Sort of maybe at a more philosophical level, I'm wondering, do you think there's anything about the study of fundamental physics that lends itself to being led astray by pseudoscience, or ideas that overpromise on their ability to explain "quote unquote" everything? I know that you've addressed these in your own way through various ideas in the multiverse and the simulation hypothesis. On my end, I've sort of noticed that there are quite a few notable physicists that entertain sort of pseudoscientific or far-out ideas. Some examples are Michio Kaku. He has a recent book out, The God Equation. I'm not so sure if there's something in physics that deserves to be called that. There's Brian Keating, who's entertained geometric unity, an alleged theory of everything that both you and I have had a chance to respond and refute, and he continues to endorse that. And then even at the highest levels, you have Frank Wilczek, who's a Nobel Prize-winning physicist, and he recently went on an interview with Deepak Chopra. And so just with these sort of examples, I just wonder if you had any comments that maybe, is there something about fundamental physics that leads people into these sort of, far-out territories?
I think the brief answer is I think yes, but it's you have it backwards. I think that the people who are drawn to fundamental physics are the people who are responsive to that kind of question to begin with, and I think if you look at many of the questions that are currently being addressed in the foundations of physics, those were questions that were previously considered to be the realm of religion. Like, how did the universe begin? Free will, maybe. Does the past still exist? What happens to information after we die? How will the universe end? All that kind of stuff. And so this whole discipline is like as close to crossing over to religion as you can possibly be with science. And some people go a step too far. Let me put it this way. But it's difficult.
I see. Do you plan on in your a lot of your work is sort of, I guess, responding to these sort of pseudoscientific ideas, I guess. Will you be planning to also further address these issues, or is that something that's sort of you don't want to touch with the 10-foot pole, so to speak?
Well, I'm presently writing on my second book, and it's about this border between the science and the pseudoscience and the religion on the one side and the philosophy on the other side. And I'll make an effort trying to point out we know that far, and this stuff you can believe if you want to, but science doesn't actually say anything about it. But I don't think about it necessarily as a negative thing. I think it's very inspirational for a lot of people, and one shouldn't underestimate this. Like, if you think of something like the possibility of parallel universes, so it's not science. in the sense that there's no evidence these actually exist. But it's like with God, science doesn't rule it out either. So if you want to believe it, you can believe it. It's not wrong. And I think that's an important point to make, and that's what my new book's about, brief in a nutshell.
Great. All right. Well, I think that's a great place to end. It's great to know that you're coming out with another book. We've learned so much about you and your work here today at Google, and it was great having you, Sabine.
Thanks for having me.
Great. Oh, okay.